Alright, hey guys, so in this video I'll be going through the proof of the quotient rule. So let the difference quotient be ux vx. So we will prove this by the limit definition or first principles, as you will understand it. So we know that the derivative of a function is defined by this limiting process. Plus delta x minus fx. So because our function here is ux over vx, so we let fx be ux vx. So this will become the derivative of ux vx. And then we will replace the respective terms here with the difference quotient. So this is like that. So ux actually adds the small quantity change, and then the vx, the norm also shares the same thing. Right, so like that. And then this fx, because it's replaced by ux vx, so it is replaced as such over this whole delta x. Right, so what I would do here is to make them the same, make this numerator change into the same denominator, so we express them in a single fraction. Right, so let's head on to it. So okay, just assume this is on the left, right? Because okay, later it'll take up a lot of space. So delta x. So because this one, the first term has to multiply this, as we know, then this term multiplies by this term. Then the top and the respective top terms must share the multiplied term. So it will become like this. This one is quite elementary. So ux plus delta x and then vx. Because you already express them in the same denominator, the same base already, right? So you can express them over a common denominator. Right, so this, and then don't forget the denominator for the entire thing. Right, so in here it looks complicated, right? So actually what I would do is I will move this thing out into another space, so it will look like this, delta x. And then because this has been taken out, it has been simplified into just this top numerator. So it will actually become ux plus delta x vx minus ux vx plus delta x, and then this. Alright, so this is by itself, and then it multiplies by the 1 over this denominator that we have taken out. Right. So, alright, let's now leave this, just leave this aside, and we'll just focus on this. Alright, so what I would do is I would actually minus each of these terms by ux vx. So this actually becomes like this. And the thing is, we can separate this into two fractions, so it looks more digestible, right? So ux plus delta x vx minus ux vx. So there's a lot of brackets going on, and then this is delta x minus ux vx plus delta x minus ux vx. So this is by itself, and then delta x, this minus sign more apparent, and then this is untouched. Right, so next step, because this term here and this term here has this common term vx, so what we can do is we can factorize them out. It also applies here, right? Because the common term here and here is ux and ux. So what we can do is we can factorize them out into vx ux plus delta x minus ux as such. Delta x. Right, so this thing is the same. Right. So, okay. So, actually here we can, because this differentiation is linear, we can actually do this. So this entire thing, I'm very lazy to just write the whole thing. It's very cumbersome. Then minus this limit. And then this is by itself. Oops. Right, another bracket. So, alright. So actually when, this is where it all crumbles down. When this delta x approaches 0, this thing simply becomes u prime x. Simply becomes v prime x. So it actually becomes just vx u prime x minus ux v prime x. And then this is the one at the front, right? Don't forget the one at the back where it's just vx squared, because this is 0, right? So multiply, so bring this on top, so it becomes vx u prime x minus ux v prime x over this vx squared. So we have proven, right? So that's about it. Very interesting. And of course, if you're interested in more proofs, I will be churning them out, and hope to see you in the next video. Thanks.